and good day. So now we are going to proceed with chapter 5, which is nuclear medicine imaging. Let's have a look at the contents for this chapter. So we have altogether 5 subtopics. Okay, the first one is we're going to look into the fundamental principles of nuclear medicine imaging, followed by the instrumentation that made up the nuclear medicine imaging setup, and then we will look into the advanced techniques that are available in nuclear medicine imaging, which are SPECT and PET, and then followed by the clinical applications, and finally the biological effects and safety to human beings. Okay. As usual, it is expected that at the end of this lesson, you will be able to understand the principles of nuclear medicine imaging, the radioactive decay and the production of the radionuclides. You will then can identify the basic instrumentation and the image characteristics for nuclear medicine imaging. It is also expected that you will understand the methods, the techniques available in nuclear medicine imaging. Here we specific to be the SPECT and PET techniques, followed by able to identify the several clinical applications, and finally to create the awareness of the biological effects and safety requirement of the ionizing radiation in nuclear medicine imaging. So let's start with the first topic, which is principles of nuclear medicine imaging. So when we are talking about NMI, in short, nuclear medicine imaging, it is actually has a specific attribute that makes it different with the previous imaging techniques that you have learned. For example, X-ray, ultrasound, and MRI. This is because the NMI will produce the image of the spatial distribution of the radiopharmaceuticals which is introduced or injected into the body. Rather than for example, X-ray or ultrasound or MRI, they will produce the anatomical map of the body. So that is why when you map to the chest, you can see the figures of or the body of that patient, except that it will only show to you the bones anatomy. Okay. Now, if for example, okay, if our body have the cell swelling, or if there is a formation of edema, or there will be a tumor enlargement and metastasis, or any changes in tissue morphology, so this kind of situation, okay, health situation, can contribute to the changes in the physical properties of the tissues. Okay, so the nuclear medicine can detect these early indicators of diseases by imaging the uptake and biodistribution of radioactive compounds. Okay, in this case, it is injected or introduced into the body, but in a very limited amounts, usually in nanograms, either inhalation into the lungs or by direct injection into the bloodstreams, or through the subcutaneous administration, or by using oral administration. So these radiopharmaceuticals, we also call it as radio tracers. Okay, it trace these early diseases. Okay, and it is actually consisting of a chemical substrate and linked to the radioactive element. So any abnormal tissue distribution or an increase or decrease in the rate at which the radiopharmaceutical accumulates in a particular tissue can be as a strong indicator of the disease. Okay, radiation in NMI or nuclear medicine imaging, it is actually not in the form of X-ray anymore, but it is actually in the form of gamma rays. Okay, and it is comes from the radioactive decay of the radiopharmaceutical, and it can be detected by using a specific device, imaging device, which called as a gamma camera. So we will look into figure 1, which shows the basic principles and instrumentation that involve the image formation. Okay, so the figure 1 here will show the radiopharmaceutical that is being localized in a specific organ or targeted organ in the body. So let's have a look, figure 1 here. Okay. So imagine we have this system. So we have a gamma ray which will be injected through the or targeted on the specific organ in the patient's body. So in this case, the system is trying to detect a brain tumor. Okay, so the brain tumor will shows up as an area of high signal intensity. Okay, this is an example from the SPECT. SPECT is actually stand for single photon emission computed tomography. Okay, so this is actually the general schematic of the instrumentation setup for NMI. Okay, by using the gamma camera. So we have a colorimeter. This is familiar to you guys, I believe. The only difference is that we have the scintillation crystal and we have the additional photomultiplier tubes. So this is actually photomultiplier tubes act as the detector, and then because we have several of tubes or detectors here, so we will have several analog output that will be or needed to be converted to digital before can be processed by the computer. So the end result will be the image, the multi-slice images like this. Okay. Now about the decay of the radioactive. Okay, it produces the gamma rays and it will emanate or distributed in all or scattered in all directions. Okay, so the attenuation of the gamma rays in tissues, it happens exactly the same as the X-rays that we have learned. So we know that it will have the photoelectric interactions as well as Compton scattering that we have discussed previously in chapter 4, and we also have the coherent scattering, but this one we omit from our discussion. So basically it is the same tissue interactions, okay, like in X-ray. So in order to determine the position of the source of the gamma rays, okay, the collimator will be placed between the patient and the detector, so that only those components of radiation that have a trajectory at an angle close to 90 degrees to the detector plane are recorded. So if you can go back to previous slide here, so you can see that almost any gamma rays that is almost 90 degrees to the detector that can be detected, okay, by the system. Okay, so to record the image, the scintillation crystal will be used to convert the energy of the X-rays that passing through the collimator into the light. So you know collimator, it helps to focusing the X-ray, or sorry, the gamma rays, okay, But here for the NMI, we have another tool, which is the scintillation crystal that convert the energy, okay, into light. Okay, so these photons lights, okay, are converted to electrical signal by using the PMT. So from the light, um, we need another special detector that will convert it into electrical signal in the form of voltage. Okay, and then the image is formed by analyzing the spatial distribution and the magnitude of the electrical signals from each of the PMT. So we have multiple PMT tubes. That is why we will have multiple analog signals. Okay. Now the planar nuclear medicine images are characterized in general as having a poor SNR and low spatial resolution. Like this is quite big, approximately to 5 millimeters, but it has extremely high sensitivity, thus able to detect a very small amounts of radioactive material, and it has a very high specificity because high specificity can ensure that only the targeted organ that is injected with the radioactive elements that can be detected. Okay, now in terms of the three-dimensional NMI images, okay, it is produced by using the principle of tomography. So principle of tomography, if you still remember, it has a rotating rotating for the NMI. It has a rotating gamma camera. So if you can compare with the previous tomography, computed tomography in chapter 4, we have a rotating X-ray source. Okay, so as for the NMI, this technique we call as single photon emission computed tomography. Now, we will look into figure 2 later on. So, oh no, sorry, we already seen the figure 2, which shows the scan of the brain tumor using SPECT. Okay, the most recently developed technique in NMI is positron emission tomography, or in short PET. Okay, so this is based on the positron emitting radiopharmaceuticals. Due to the nature of the processes involved in positron annihilation and subsequent emission of two gamma rays, so PET has a quite extra sensitivity. Okay, so this is an advantage as compared to SPECT. Okay, now, okay, I forgot to mention about this. So positron is actually, okay, over here is actually referring to the it's a coin term between two words, which comes from positive electron. So positive electron is positron in short. Okay. Now, in terms of radioactivity, so what is radioactivity? So radioactivity is an intrinsic property of particular isotopes that have unstable nuclei. So the phenomenon of radioactivity refers to the process whereby various forms of radiation are emitted as a result of a spontaneous change in the composition of the nucleus. So this is quite fundamental when you hear it. Yeah, you have to go to physics, back to your physics. So what is isotope? Because we said radioactive is an intrinsic property of particular isotope. So isotope is each of two or more forms of the same element that contain equal numbers of protons but different numbers of neutrons in their nuclei, and hence differ in relative atomic mass but not in chemical properties, in particular a radioactive form of an element. Again, for example, if what does it mean by this is that if we can take carbon, just a dummy example, okay? If we take element carbon, okay, if that carbon have different numbers of neutrons, okay, then that for example carbon, I can't recall the chemicals theories, just a dummy example, yeah, don't take it as a fact, okay. um, for example, carbon has the neutrons of it has a number of protons 4, but the neutrons, for example, say 6, and then another element carbon with the same proton number 4, but the neutrons is 8. So you can see that you have two different isotopes here, one with the number of neutrons 6, and another one is with 8. Okay, that's just a dummy example for you to get better understanding on this. Now, okay, if I can yeah. Now, so whether or not an isotope is radioactive depends upon the stability of its nuclear, which in turn is dictated by the relationship between the atomic number and the atomic mass. Okay, so strong neutron, neutron proton, and proton proton forces are attractive over very short distances, whereas electromagnetic forces between protons are repulsive in nature. And so the stability of a particular nucleus is very determined by the balance of these attractive and repulsive forces. Okay, for values of A, so A is the atomic mass, less than 50, a stable configuration corresponds to a nucleus with equal numbers of neutrons and protons. For heavier nuclei, for example, when the atomic mass is greater than 50, the ratio of the number of neutrons to protons required for stability increases, as shown in figure 3. Okay, so this is what does it means by here. The solid line represents the number of protons and neutrons required for nuclear stability, and the dashed line represents equal numbers of protons and neutrons. Okay, the radioactivity, okay, or activity labeled as Q of the radionuclide. It can be defined as the number of nuclear disintegrations per unit time. So as for the N nuclei of a particular radioactive isotope, so the equation that you need to use is here. Q equals to negative dN over dt, and it is actually equals to lambda times n. So lambda here is actually the decay constant and has the unit of per second here. And radioactive is actually measured in the units of curies, Ci, or more conveniently in millicuries, where 1 Ci equals to 3.7 times 10 power of 10 disintegrations per second. Okay. Now, some of the texts, older texts, they use becquerels, BQ. So, where 1 BQ is actually the same as or equal to 1 disintegration per second. So, equation 1 here can be solved to give another second equation, which is n equals to n naught exponent negative lambda t. Here, the n naught is actually the number of nuclei at time when t is equals to 0. So this is quite, I know, a lengthy explanation, but we're going to have a look into examples later on exercises. Okay, so I proceed with this explanation. So when calculating the time dependence of radioactivity within the body for a nuclear medicine scan, the biological half-life of the radionuclide must also be considered. In many cases, excretion of the radionuclide from biological tissue is also an exponential process which can be characterized by a decay constant. Okay, this is the label for it, lambda bio, and corresponding half-life, which is tau bio. Okay, this is symbol of tau. The effective half-life, okay, of radioactivity within the body is given by this equation. I'm not going to focus on this equation, and it's just that the fact that the effective half-life is always less than the shorter of the two half-lives, and the decay, sorry, and the corresponding half-life. Okay, so let's see one exercise here on how to calculate if you have the half-life of 99 mTc. So Tc is, we're going to look into what is Tc. When the Tc is, when the half-life of 99 mTc, so 99 m is referring to the isotope that we discussed just now. Okay, so Tc is an element, is 6 hours. So how much time when the 1/16th of the radioisotope remain? So there is a solution for this. Okay, yeah, this is the solution for this. So you need to calculate one by one. First of all, okay, you need to start with the decay constant and the half-life. Okay, so this is the formula. If we can go back to here, yeah. Oh, sorry, I skipped this one. No wonder. Okay, can I explain a little bit about this one? Okay, no wonder we skipped to equation 4. So what is the half-life? Okay, so the half-life of a particular element corresponds to the time which is required for the radioactivity to drop to 1/2 of its current value. Okay, so it is shown here in figure 4. So the half-life of the element, so the element will decay in exponential form. So the half-life is counted, if we consider the ratio here, n over n naught, half of it is here. So this is counted as the half-life of the specific element here. And we have the formula to calculate it, which is ln 2 divided by lambda. So this is the formula that is used in the first exercise just now. Okay, you need to rearrange because the lambda is not given. Okay, but we have the half-life value. Okay, so I can go back to our exercise just now. Okay, yeah, so I'm not sure if I can write down anything. Yeah, I can write something here. So this is the formula. The original one is actually this T or tau half. Okay, it is actually equals to 0. Okay, sorry, it's taking time to write down because I'm using my fingers. Okay, and it's quite ugly, but I know you will understand it. Okay, over, so we have here is the lambda. So now we have the half time value, which is 6 hours. Okay, so when you calculate this, okay, you want to get the decay constant. The lambda here is not wavelength, but it is referring to the decay constant. Don't get confused. Okay, so when you plug in the value, you will get 0.1155 per hour. So just make sure that you notice the unit. Okay, it's important to make sure that the units you are using is correct. Now if we apply the first equation that we discussed previously, okay, not the first equation, I think this one is the second equation, yeah. N over N naught equals to exponent, so if I can write down, it is actually similar to this one. Okay, this is taking edges. I hope you can bear with me. Okay, so this is how it is. Okay, lambda t. Okay, yeah, this is how we write it down in the form of mathematical equations. Okay, now we know that the question tells us N naught has reduced to 1 over 16th of its values. So basically we have here NT over N naught is actually 1 over 16. So you just plug in this value into the equation here, and if you calculate correctly, okay, you will be able to get the T. Okay, because we are interested to get the T. I'm not going to explain on how to get T because this is only simple mathematics formula. Because you want to get the T, you have to eradicate the exponent. To eradicate exponent, you have to make it change it to ln. You ln both sides. So if you ln exponent, you will get the power of exponent here, okay, to become like this. Okay, you can get the new form of it, and from here you can calculate the T. So the T, if you compute it using calculator, will produce this outcome, which is equals to 24 hours. So basically it takes wait now. Okay, wait now, got it. Okay, I have put, what happened? Oh, okay, can you give me time? Okay, I would like to change this one first to automatic. Can I bring this one? Okay, cannot. So it will take 24 hours until the radioisotope remain to 1 or reduce to 1 over 16th. Okay, so that will be the solution for your first exercise. And for the second exercise, okay, this is quite a tricky question because it is given in the form of becquerel. Okay, so 1 megabecquerel. So we know that 1 becquerel is equals to okay, let's double check. I don't want to wrongly say it. Where's the becquerel? Wait now. I have, okay, this one. It is equals to 1 disintegration per second. Okay, so we're going to use this information. Okay, if I can write it down here, it is actually 1 BQ. Okay, I probably should use my iPad to write it down, but it's okay, it will take time to set up. So 1 disintegration per sorry about that, very ugly, the handwriting. Okay, disintegration per second, DPS. So 1 becquerel is equals to 1 DPS. So let's go back to our exercise number 2. Okay, exercise 2. Okay, again, the formula is still the same. Okay, this is easy to remember. So if you're wondering what is 0.693, this is actually ln 2. Okay, just in case if you are not aware, where does it come from? It's actually ln 2. Okay, yeah. Just plug in the value. So we have the half-life is 6 hours, the Avogadro's number is 6.023 times power of 1023. Okay, still using the same element here, 99M isotope element of Tc. So this next, when you plug in this value, you will get this in hours. Now, because you are dealing with the second, so you need to change it to per second. Okay, so I'm not going to show you how. You try to solve it by yourself. Okay, it's pretty simple. Okay, the question gives us the radioactivity in 1 megabecquerel. So we know that 1 becquerel, okay, okay, I have to write it down again. 1 becquerel is actually equals to 1 disintegration per second, 1 DPS in short. So if we use 1 megabecquerel, it means that it just times out with 1 mega, so it becomes 1 mega DPS. Okay, clear? So this is our equation, lambda n equals to 1 mega DPS. So from here, we want to get the n, the number of nuclei. So just divide it with the decay constant here in per second, because we are dealing in second. So that is why, okay, the megabecquerel converted to disintegration per second, the unit is second. So that is why we have earlier on the decay constant must be calculated in second. So when you plug in, this is the value that you get, and your final solution, because you are looking for the minimum mass. Okay, we want to calculate the minimum mass. So this is the formula for it. The mass of the n nuclei is the number of nuclei times mass number divided by Avogadro number. Okay. So mass number, again, you just plug in the 99 here. This is the mass number, and if you plug in correctly, you'll get 5.122 times 10 power of minus 12 grams. Okay, I hope that one is clear. It's very simple exercise. Try to do it at home. Try to do it again. Okay, now about this one, types of radioactivity decay. So this will be going to be your tutorial questions. I'm going to give me time to do it. Okay, so sorry to you guys. I apologize because I'm quite busy as well for doing other things, but I will catch up with you guys about the tutorial questions later on. So just stay tuned and be patient with me. Yeah? So this is going to be part of your tutorial question, including the metastable state, the ideal energy of gamma ray, the ideal radionuclide, okay, the technetium generator, okay, yeah. So about we're going to move into the instrumentation of the gamma ray. just now we have looked at the overall view of the instrumentation setup for NMI. You know that we have the collimator, okay, we have the scintillation crystal, coupled photo multiplier tubes, the angle position network. This is not shown in figure 1 just now, and another one is the pulse height analyzer. So we're going to discuss a little bit details on this one. So figure 8 here shows the schematic diagram of the gamma camera, which is positioned above the patient. Okay, and the distribution of the radiopharmaceutical is indicated by the shaded region within the body. So this is where the targeted organ that have been injected with the specific radio pharmaceutical agents. Okay, so here basically we have it is actually upside down, okay, the figure here. Okay, so we have the gamma rays that is injected, and then it not connected, sorry, it is scattered to the detectors here, but before it reaches to the photon multiplier detectors, it will going into the lead collimator and the scintillation crystal, and then only then it reaches to the photo multiplier tube. Okay, I'm not going to talk more on based on this figure. We check here the details. Okay, so the collimator, it reduces the contribution of gamma rays that have Compton scattered in tissues. Okay, so you know that Compton scattered, it has no useful spatial information, and some more it will reduce the as a consequence it will reduce the image of the CNR. So that is why we need a collimator. So the common geometry we have is a parallel hole collimator, okay, which is designed so that only gamma rays traveling at the angles close to 90 degrees to the collimator surface will be detected. So it is actually constructed from a very thin strips of lead through which transmission of gamma rays is negligible. So the normal pattern here is the honeycomb geometry. Okay, this is an example of the collimator lead strips. We have two general classes of collimators. The first one is the high resolution and high sensitivity, where the septa thickness is higher for the HR than for the HS. Okay, so this is the two general classes, HR and HS. If the HR, it will have the HR will have septa thickness greater than the HS. Okay, so there are number of types of collimators to magnify or reduce the size of the image. It depends on the what purpose of that collimator. So this is an example. Okay, so we have the object here and the image. So this is when we want to image a structure larger than the size of the detector. So this is the type of collimator that we are going to use. For this one is to image the small organs that close to the surface of the body. So this is the type of the collimator that we're going to use. And this is another collimator example that is used to image a very small organ, for example thyroid or parathyroid imaging. Okay, so very focusing. So now we go to the scintillation crystal. The most common gamma ray detector is based on the single crystal of thallium activated sodium iodide, or in short, null Ti. Okay, so this is basically um, the type of the crystal name. Okay, so why the thallium is used is because it creates imperfections in the crystal structures of the null, such that the atoms within the crystals can be excited to elevated energy levels. So when the gamma ray strikes the crystal, it will lose energy through photoelectric, you know that, photoelectric and Compton interactions with the crystal. So the electrons ejected, okay, by these interactions lost energy in a short distance by ionizing and exciting the scintillation molecules. So the excitation of these excited states within the scintillation crystal occurs via emission of photons within a wavelength of 450 nanometers. This is the visible blue light, which correspond to the photon energy of 4 electron volts. So the intensity of the light is proportional to the energy of the incident gamma ray. Okay, the light emission decay constant, which is the time for the excited states to return to the equilibrium state, which is 230 nanosecond, okay, for the null Ti. This means that the the sorry this means that the count rates of 10 power of 4 to 10 power of 5 gamma rays per second can be recorded accurately. So it's very short actually. So because of the decay constant is very short, so they can capture more gamma rays. And yeah, this one you can read. I want to proceed with the next explanation on the coupled PMT. Okay, here photomultiplier tubes, PMT tubes in short. Okay, it will be detected. Okay, so you know that the collimator will only accept the gamma rays and not the Compton scattered rays. Okay, then we have the scintillation crystals that we'll use to convert the gamma rays into light. Now we have the light photons, so the light photons then will be detected by the PMT here. By right, it is in the hexagonal shape, okay, hexagonal PMTs, which are closely coupled to the scintillation crystal. Okay, so this geometry gives efficient packing and also has the property that the distance from the center of one PMT to that of each neighboring PMT is the same. So this property is important for determination of the spatial location of the scintillation event using an angle position network. So there are arrays of 61, 75 or 91 PMTs. So that is the number of PMT available with the diameter between 25 and 30 millimeters, which typically used. Okay, so this is the basic design, okay, of the PMT. So the light emitted by the scintillation crystal, so this is the scintillation crystal, is converted into a current at the output of the multiplier tube. So this is just an example. It only shows the 3 diodes, okay, usually up to 10. So for every electron striking the diode, a significantly greater number of I cannot see this one because of my yeah, you can read that one. Yeah, I can see it. So let's talk about angle position network. Okay, so the PNTs situated closest to a given gamma ray induced scintillation in the crystal will produce largest output current. Okay, So we know that PMT is used to convert the light into electrical signal. In this case, it converts into the current output. Okay, so by comparing all the magnitudes of the currents from all the PMTs, okay, the location of individual scintillations within the crystal can be estimated. So this calculation is carried out by using an angle logic circuit. So it is actually named after one of the pioneers in the development of the gamma camera, Hal Anger. Okay, I hope I pronounce it correctly, his name. Okay, so this network produces four output signals. So we have X plus, X minus, Y plus, and Y minus. And this is the relative magnitudes and signs of which define the location of the scintillation event in the crystals. Okay, Figure 13 shows two of the four channels of the network. Okay, this is one version of the electronic network used to estimate the location at which a particular gamma ray strikes the scintillation crystal. Just for the simplicity, only X plus and X minus channels are shown in their entirety, and only 7 PMTs, 1 to 7, yeah, this 1 until 7 PMTs are drawn. So the magnitude and polarity of the outputs X plus and X minus determine the position. I cannot read this. I hope that you can see it and read it by yourself. Sorry for that. Next, on the pulse height analyzer, or PHA. So just now that we know that we have the X plus, X minus, Y plus, and Y minus components. So these will be summed up, okay, and brings to the new term, which is the Z signal. Okay, so this Z signal will be sent to the pulse height analyzer, PHA. So the PHA will compare the Z signal to a threshold value, which for the 99 MTC scan that corresponds to that produced by the gamma ray with the energy of 140 keV. For example, if the Z signal is below this threshold, it is rejected as having originated from the gamma ray that has been scattered in the body, and therefore has no useful spatial information. Okay, now we will have a look into an image characteristic. So the characteristics of the nuclear medicine scans are a low SNR and poor spatial resolution, but an extremely high SNR compared to other imaging modalities. Okay. So various forms of data post-processing are used to increase the image of to increase the SNR image, although this will degrade the spatial resolution. So we are actually talking about how the image characteristics in NMI is different with the X-ray image characteristics. Okay, because the NMI will have low SNR and poor spatial resolution. Okay, but high contrast. So in terms of SNR, okay, so we know that for the NMI, okay, you don't know yet, okay, the SNR is actually proportional to the square root of the total number of counts, okay, in NMI. We are talking about NMI now, and therefore the greater number of gamma rays detected, the higher the SNR. Okay, so factors that will affect the SNR include the following. Okay, the amount of radioactive dose, the effectiveness of the radioactive at the targeting specific organ, the total time over which the image is acquired. So the greater the time, the larger the number of X-ray detected. Tissue attenuation. Okay, if the image is closed to the if the organ that being imaged is close to the surface of the patient, so less attenuation detected. Okay. So for different radionuclides, higher energy of gamma ray emitted, the lower the attenuation in tissue, the higher the image SNR. Okay. In terms of the intrinsic sensitivity of the gamma camera, okay. So if we increase the scintillation crystal thickness, the SNR will be increased because more gamma rays are detected. Okay, but this will decrease the spatial resolution. Okay, and another one is post acquisition image filtering. So okay, the processes of the final image will affect it. Normally this process consists of just apply a low pass filter, but this filter will reduce the contributions of high spatial frequencies and then make it reducing the noise level, but will affect the image in terms of it becomes blurry. Okay, so these are things that are very specific factors that can affect the NMI SNR images. Now we're talking about spatial resolution. Basically, there are four major contributions to the spatial resolution of a nuclear medicine scan. Um, the first factor is the intrinsic spatial resolution of the gamma camera. This excludes the collimator. Okay, the second is the geometry of the collimator. The third factor is the degree of the Compton scattering of gamma rays within the patient. And final factor, which shares with the SNR, is post-acquisition image filtering. So I'm not going to discuss details on this. You can read by yourself the explanation of this. Okay, and this is speaking of the SNR. So we know that SNR is high in NMI image. It has high SNR but low SNR and low spatial resolution. Okay, why there is a high SNR in NMI? Because there is no background signal from tissues. Okay, because we're only targeting a specific organ or specific area within the body. So the radio active is not distributed on other parts that is not out of our interest. Okay, so the image SNR, okay, it is equal to the image of SNR, but the presence of the Compton scattered gamma rays that contribute to the degradation of the image SNR. So if the spatial resolution is poor, okay, the SNR is reduced because the image blurring will cause the signal bleed from the areas of high signal intensity to those where no signal should be present. So this phenomenon we refer to as the partial volume effect, and is particularly obvious for small structures. Okay, post-acquisition processing using low-pass filters also increase the SNR as we discussed previously, but it will affect the SNR. So these low-pass filters is either increase the SNR if the SNR increase, but outweigh the loss in spatial resolution, or it can decrease the SNR if the loss in spatial resolution is very dominant. Okay, so we will proceed with the advanced techniques in NMI on the following weeks. So I will let you know when our online class will be available. So we're going to finish up 5.3 as well as 5.4. Okay, let me scroll it first. 5.4 is the application, clinical applications. Okay, here. And so for your tutorial, we'll cover the radio radionuclear types, radioactive types, and the biological effects and safety. Okay, so yeah, we only will have another one class, probably. I will tell you later on whether it is online class or offline class. Okay, so for now, I hope this one clear for you guys, and it will help you to do your study on chapter 5. And yeah, wait for my announcement on tutorial questions. Okay, alright, I think that's all for now. We'll see you around later on. Have a good day ahead. Bye bye.